A rolling mean can leak the future by one row. Pandas makes it easy to build the feature safely once you know the alignment trap. By the end, you'll be able to build a workflow like this, which aligns rolling features to past dates without leakage. I'm Professor Pi, teaching AI foundations with simple Python. Rolling features are everywhere in time series work. We grab a rolling mean when we want a smoothed view of recent behavior, something that tames noise and gives models context about local trends. But with time series, past versus future is sacred. If a feature sneaks tomorrow into today, your backtest will lie, and your production model will fail. That's the rolling feature leakage problem. What we want are features that only see history, validation that reflects real difficulty, and models that generalize to new dates. The subtle trap comes from where Pandas puts the aggregated value. A centered window averages across past and future, then tags that number onto the center timestamp. That looks neat for smoothing, but it quietly pulls tomorrow into today's feature. Imagine a 5-day sales series. The centered 3-day average for January 2nd includes January 3rd. That's exactly the kind of contamination we must avoid. We will build a short pipeline that first shows the leak, then fixes it by shifting and by enforcing minimum history, and finally compares the leaky and safe signals with a tiny backtest. The code is deliberately small, so you can see the dates and numbers that reveal the leak. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We need to show the leak on a tiny sequence so the misalignment is visible. This snippet shows how a centered rolling mean quietly leaks future values into today's feature. The Pandas date range builds 5 consecutive days of sales, so the pattern is easy to inspect. The data frame assign call computes center average with the center option set, which aligns the label on the day being predicted, while still averaging the previous and next observations. Because the future day participates, the value stored at index 1 is already contaminated with information from January 3rd. The printed 12.67 reveals that the January 2 feature is inflated by including January 3 sales, so it cannot be used safely. Next, we need a simple move that removes the current and future observations from the window. This example refactors the feature, so the rolling mean only considers prior sales before today's prediction. The DF data frame from earlier is reused, and Pandas assign creates a new past average column by first shifting sales down one row. The shift removes the current observation from each window, and the rolling call with min periods equal to 1 then averages the available history without forcing full windows. We capture the row for January 3 to make the effect tangible, showing that the feature now reflects only January 1 and 2. The printed 11.50 confirms the safe feature is purely historical for January 3, so it is valid for modeling. Now let's compare the two signals directly to see how much the centered signal drifts. This code compares the leaky and safe signals to expose how far a future latent feature drifts from reality. Computing diff as center average minus past average isolates the inflation created by sneaking tomorrow's sales into today's estimate. The chained absolute and index maximum call pinpoints the row with the greatest distortion, and diff.lock retrieves the signed gap for that same row. Using df.lock to fetch ds supplies the calendar date so we can explain the discrepancy in plain language. The printed 4.00 on 2023-01-04 proves the centered value overshoots by 4 units, quantifying the leakage in one glance. After we fix alignment, we should also decide whether to emit values before enough history exists. This snippet hardens the safe feature by insisting on complete history before emitting rolling averages. It reuses df and lagged, but now the new stable average column applies rolling with min period set to 3, so partial windows remain missing. The min periods guard ensures that early timestamps wait until 3 prior sales exist, which prevents flimsy warm-up values from entering training. Counting the non-null rows gives a quick diagnostic on how much data survives the stricter rule. The printed count shows only fully supported rows progress, highlighting how min periods protects the pipeline. Finally, we should measure how the leaky and safe features perform when we pretend to predict held-out dates. This example wraps up by comparing leaky and safe predictions with a simple mean absolute error backtest. The valid data frame aligns the target sales with center average and past average after dropping any rows still warming up. Each MAE call then reports how close the signals stay to reality when only historical inputs are permitted. Because the leaky series already saw the answer, its score looks unrealistically sharp, while the safe series reflects true difficulty. The printed metrics contrast a too good to be true 0.67 with the honest 3.94, proving the leakage fix preserves credible validation. If you take this tiny example into a real pipeline, map the toy dates to your timestamp column, produce lagged rolling features from live historical snapshots, and gate features with the same min history rule used in training, that keeps your validation honest and your models robust in production. Recap: centered rolling aggregates can leak future information, shift the data, so each window only looks at prior rows, and require a minimum number of prior observations to avoid weak warm-up values. Those 2 steps give you features that are safe for backtesting and reliable in production. Next step: scale this exact approach to a larger dataset and add a rolling cross-validation so you can measure stability across many holdout windows. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.